Alright, this is another MCA lesson for 8th grade, and today we're going to talk about sequences. We've already covered this a little bit, but today we're going to take it a step further like we do with most things. And this is something that appears on the MCAs, so we want to make sure we at least have the basics down and look at some of the things we might see on the test. So there are two basic sequences that we're going to be talking about, and the first one, well, first let's remember what a sequence is, Sequence is an ordered list of numbers called terms, and they follow a certain pattern or rule. For instance, this one, 3, 6, 9, 12, and it keeps following that pattern. Okay? Now in this one we are adding 3 to each term. 3 plus 3 is 6, 6 plus 3 is 9, 9 plus 3 is 12. If we kept going, 12 plus 3 is 15, and we would keep going in that direction. So this sequence is an example of an arithmetic sequence. This term is also arithmetic. Usually when we describe the sequence, it's pronounced differently, but we're not too worried about the pronunciation. But basically, we just need to remember what it is. An arithmetic sequence has a constant difference between terms. So by subtracting consecutive terms, we can find that difference. So 6 minus 3 was 3, 9 minus 6 was 3, 12 minus 9 was 3. Okay? So the way to remember what this one's all about, think about, it starts with an A, and adding starts with an A. Okay? So between each term we're going to be adding. Now we can't let that confuse us with the next example that I'm going to pull up right here, because arithmetic sequences don't always have to go up in value, they can also go down. So for instance, 7, 2, negative 3, negative 8, and keep going down that path. Now this one we're subtracting 5 each time. 7 minus 5 is 2, 2 minus 5 is negative 3, negative 3 minus 5 is negative 8, and we keep going like that. But remember that subtracting is the same thing as adding the negative, or adding an opposite. So 7 plus negative 5 equals 2. 2 plus negative 5 equals negative 3. So we can still get the terms like that. So we're still adding, but we're adding a negative, and you just have to figure out what your constant difference is. Okay? So arithmetic sequences, they involve adding either positive or negative numbers. So the other type of sequence that we're going to focus on will be this type. Okay? So describe the pattern in the sequence and find the next 3 terms. We won't find the next 3 terms, but we do at least want to see what this pattern is. And it goes from 1 to 3 to 9 to 27. Looks like in between each of these we're multiplying by 3. 1 times 3 is 3. 3 times 3 is 9. 9 times 3 is 27. If we did 27 times 3, we should get 81. And then keep going like that. Okay? So this sequence, and this would be example 2, is a geometric sequence. A geometric sequence has a constant ratio between terms. Okay? So, I don't have an example, but just like the last one, this one increases in value. We could probably, well, not probably, we could also have, let's say we had 8, 4, 2, 1. Okay? We could also be doing this. Looks like we're dividing by 2 each time. Same thing as dividing by 2 is multiplying by 1/2. 1/2 times 8 is 4, 1/2 times 4 is 2, 1/2 times 2 is 1, and so forth. So geometric sequences is all about multiplying by a constant ratio. Okay? So they don't always have to increase either if we're multiplying by a fraction. Okay. The terms of a numerical sequence have a position and a value. The position of the term, such as first, second, third, is often called the number of the term. Okay? The number of the term is found by counting and may be abbreviated with the letter n. and the value of the term, which is the actual number that appears in a sequence, may be abbreviated with the letter A. Okay? So, all of that mess that we just talked about, or I just read, is summed up right here. This was our first sequence we looked at. It was arithmetic because we added 3 in between each term. So these are the values of each term: 3, 6, 9, 12, 15. And this just tells me, okay, my first term is a 3, my second term was a 6, third term was a 9, fourth term was a 12, fifth term was 15. Okay? And why that's going to become something we're going to want to see is because we can also graph these sequences. Okay? So we treat it like our XY charts basically. So if we rewrite it, it would be N and A. So what term? First term was 3, second term was 6, third term was 9, fourth term was 12. So if we treat these like points like we do for our xy's, we can graph them, and we can do the same thing for that geometric sequence that we saw earlier too, where we multiplied by 3 each time. Okay? So for this one, we go over 1 up 3, over 1 up 3, next one over 2 up 6, over 2 up 6. And what we're finding out with the arithmetic sequence is that it follows a straight line pattern. So these arithmetic sequences, they directly relate to what we were talking about before, or a couple days ago, y equals mx plus b, or that slope formula, slope-intercept formula. So just realize that with arithmetic sequences, we're going to have a straight line. However, our geometric sequence will not. Okay? It doesn't have a constant slope. We can see if we connected these, we'd have some sort of curve, and it would not be a straight line. Okay? So that one was first term and was a 1, second term was a 3, so over 1 up 1, over 2 up 3. And it doesn't follow that nice pattern that an arithmetic sequence would follow. Okay, so let's take these are the same sequences right here, and what we're going to do is come up with a formula that describes this sequence. And this is where it gets a little tricky, because yes, in between each term we are adding, but when we look at coming up with a formula relating the inputs to the outputs, there will be no addition involved. Okay, so let's remember we had N and A. So our number of the term, 1, 2, 3, 4. So this was our first term, second term, third term, fourth term. And our first term was 3, second was 6, third was 9, fourth was 12. So now, yes, we are adding as we go down or across in that sequence. We're adding 3 each time, but we want to look input to output. So what are we doing from here to here? And we are actually multiplying by 3. So it looks like A is going to be 3 times whatever N is. Alright? So this was the actual term, this was the number of the term. So whatever the number of the term is, A should be 3 times that number. Let's check it out. Our fourth term is 12, so if I put 4 in for N, 3 times N, or 3 times 4, I should get 12. 3 times 4 is 12, okay? If I put in 5, because our next term should be 15, we add 15. If I put 5 in for N, 3 times 5 gives me 15. That would be our next actual term, or value basically. So this would be the equation, or formula, to come up with the next, or any term in that sequence. Now, if I wanted to, I could find the 500th term. It would be 1500. 3 times 500, and 1500 would be that term, okay? So that's that one. So keep in mind that the formula for an arithmetic sequence will involve some sort of multiplying, which is kind of backwards. because an arithmetic sequence involves adding between terms, but the formula involves multiplying by a constant ratio. Okay, so, or your constant difference, sorry. Now the constant ratio was the geometric sequence, and this one, our constant ratio was times 3. So let's look at what we have here. This one's even a little bit more confusing. N and A, our first term was 1, second term is 3, third term is 9, and fourth term is 27. Okay, so what are we doing from this side to this side, input to output? It's not quite as obvious. However, let's look at the diagonal, and well, here let's. First thing you want to do with this one is you want your constant ratio, which was 3. You want that written down. So A is going to be 3. And then for the geometric sequences, you're always going to have something in the exponent. So we got to look for something we can put in the exponent. And we have to relate it to our input. So, for instance, this is 3 to the first, right? This is 3 to the second, 3 to the third. Our next term should be 3 to the fourth. 1 is 3 to the 0, because anything to the first power is 0. So we know we're going to have 3 to the something, and there's going to be an n involved. If I just put n right here, that would be, okay, first term, 3 to the first power is 3, so that doesn't match up. How do I make this so that we get a 1 here? Well, we want to get 3 to the 0 power. So 3 to the n minus 1 should get us there. Now if I put 1 in for n, I get 3 to the 1 minus 1, which is 3 to the 0. And 3 to the 0 is 1, and that's what we want. Okay, so it works for that one. Let's put 2 in. 2, we should get a 3 as an output. 3 to the 2 minus 1 is 3 to the first. 3 to the first power is 3. Good. It's working out so far. Let's try 3. 3 to the third. So we want to get 9 here when we put n in for 3. Or 3 in for n. So 3 to the 3 minus 1 is 3 to the second. 3 to the second is 9. Good. Okay? So if we did put it in, if we put 4 in, we get 3 to the 4 minus 1 for our term. 4 minus 1 is 3, and that would be 3 to the third power, or 27, and it would work out. So geometric sequences, when we are finding an equation, it works out that we need something in our exponent that relates to the input. And then remember, this one, you end up having a multiplying scenario for your arithmetic. Even though this one involves the constant ratio of multiplying, this one involves a constant difference with adding. Now, how to find formulas like these, that will be on your formula sheet on the MCA, so that'll help you kind of see the difference between them. This is the hardest part, and you kind of got to mess around with it, but it is kind of fun. It's kind of like figuring out a puzzle. But these are the last 2 examples I had for today. So that is sequences.